morning. Happy Friday. Or maybe unhappy Friday. I don't know if you're coming around to Fridays, David, or what. But
I got a whole bunch of stuff I should be doing, and one specific thing I want to be doing, and I need to get the stuff I should be doing done first before I can do the thing I want to do. So
it is such a classic dilemma. Every little bit of free time, I'm like, but I want to be doing this. Oh well. All right. So I did start marking. I'm not finished marking, so I'll finish marking those this afternoon. Your tests. So I'll send out a message with the grade scope when they're done, so you can check them out. But I'll, like the other tests and for the quizzes as well, I'll post your like overall test 2 grade on Moodle once I'm finished. So yeah, okay. So today we are doing related rates, and I hate to say it, but it is, in my opinion, the hardest section of this course. So I want to take it nice and slow. It's not going to feel nice and slow to you guys, but it's all we're doing today. So we're only doing related rates because I want to show you guys all the techniques, and then it's going to be about practice. And if you've had a look on Moodle, I have posted some extra practice problems. So those were my notes from when I taught the course before. So now I decided, okay, I'm just going to give you guys those so that you have more problems to go through with kind of worked out solutions. And then we'll go through some different problems in class. And then I also posted a Khan Academy video. He does a really good related rates example that I found really useful. So I've posted a lot of related rates resources. Now it's in your hands, of course. Not fun to be hearing as a student, but here we go. Okay, so related rates. So section 3.9 is on related rates. Okay. So the thing about related rates is, well, we know that the derivative is the rate of change, right? And so what we're actually saying is that we're going to have related derivatives, right? And so sometimes one derivative might be easier, or one rate of change might be easier to find than the rate of change that you're actually interested in, right? And especially in our case, one rate of change will be given, and then we need to use it to find a different rate of change. So the key here is, well, there's a couple of key things to keep in mind, but recall that a rate, right, or a rate of change is the derivative. Okay, so for us, for these related rates, right, in related rates, which in your mind, I want you to think kind of related derivatives, and I think that is a little bit more helpful. Related derivatives, I'll put that in brackets. We will be given one rate of change, so we'll be given one derivative, and then we use it to find another derivative. So in related rates or derivatives problems, we will be given one rate of change, which we will use to find another rate of change. to find another rate of change. Okay. So that's for us, and I want to kind of introduce kind of the real world application, but for now, just to kind of clear your head, right? You'll be given a rate, one derivative, and then we have to find another derivative. And so what we need to do is we need to find a function, right, that relates these two derivatives. Okay. This means we will need to find a function that relates these derivatives. Okay. So kind of weird, okay? But in general, so now I'm doing my kind of general life blurb. Why do we need related rates? Well, sometimes, right, kind of the same scenario as in the questions, sometimes there will be rates that are easier to measure, right? It's potentially easy to find how quickly or at what rate the volume of a balloon is changing. That's our first example. But it's harder to measure how quickly the radius of the balloon is changing. But we do understand that, okay, when I pump air into a balloon, right, it will expand at some rate, especially in that the rate of the radius is going to expand kind of somewhat proportionately to the volume that I'm putting into it, right? And so we understand that relationship, but we need to kind of establish it and use it to find the rate that the radius is changing in our first example, right? So we'll start there, just to kind of show you the ropes. Okay, but in general, there will be times when finding the rate of change might be difficult. When finding the rate of change might be difficult. Okay. So instead of measuring the rate of change explicitly, right, like I could probably hook my balloon up to a machine that tells me how quickly I'm changing the volume, right? How quickly is the air entering this balloon, right? Whereas sitting there and having some sort of device to measure how quickly the radius changes sounds difficult, right? And so instead of measuring, and I'm going to try to write a little bit nicer. I've been writing a lot this week, and so for some reason my writing just goes out the window. So I'm going to try to focus up here. Instead of measuring, so much for that, the rate of change explicitly, we can use related rates to solve the problem. Okay. So for us, right, we're going to compute, so we compute the rate of change of one quantity in terms of another quantity, which is going to be given, which we already kind of said. So maybe what I want to do is just bring in the step-by-steps, because I kind of went off book there. All right, so the handout does have a little kind of blurb, blah, blah, but I want to talk about this problem-solving strategy. Some of it sounds a little wishy-washy, but we'll talk about it. Okay, so step one, read the problem carefully. It kind of goes without saying, but hey, step one, done. Okay. If possible, draw a diagram. So this is going to help you to visualize. And for me, at least when I see a related rates problem initially, if I start kind of sketching it out to try to get an idea, because at least for me, these relationships don't come easily, right? I need to kind of look at it and see what's going on, figure out what I've been given, how can I kind of knit these things together and kind of make it happen. So then after drawing a diagram, so I would say that's probably the most important step. And of course, for marking your work, even if you're not able to get to an answer, that's okay, right? Start by drawing this diagram. I'll give you marks for that, right? I'll give you marks for each step, even if you're not able to get to an answer, because I know that this stuff is tricky. So don't worry. Then we're going to introduce notation. Now, sometimes it'll be obvious, sometimes not so much. For the test, so we do have a test 3 and of course the final exam. I'll prepare you with the practice test, right? So that you have a good idea of kind of what to expect. I'm not throwing any related rates curveballs. That's not my style. This stuff is tricky enough. So the notation at the test point should be obvious, but and then of course we kind of make notation for everything that's on our diagram. So then we want to, so we'll be given a rate. So you'll want to express that as a derivative. Okay. Then what we want to do is we want to take a step back and say, okay, so I have this derivative that I want to relate to another derivative that I eventually want to solve for. So what we need to do is we need to set up just an equation or a function that relates those two quantities, right? So in terms of the balloon example that we're going to do, right, we can relate the volume to the radius by some formula, right? And whatever formula you need, I will either give you, or it will be a triangle so that you can use the Pythagorean theorem. So for volume and that kind of stuff, I would give you that formula. Because that's sometimes the hardest part, finding the formula that relates these two. So that's kind of, okay, now we're out of the woods. So once you have an equation that relates these two quantities, then what you do is you can use implicit differentiation often, or differentiate explicitly, but usually it's implicit, which you'll see. But you're going to differentiate both sides of the equation, and then it's not until the very, very last step that you can substitute in the given information and solve for the rate that you're interested in. And so what I want to do is I also have a little warning here on the handout, okay, that I do want to grab here, maybe shrink this up just a bit. Okay, so here, it's not until the very, very last step, and you'll know what I mean once we see an example. It doesn't make sense now, but you will be making substitutions such as the rate that you've been given, and then there will be other quantities that you'll be given as well. You do not make those substitutions until the very, very, very end, okay? So because otherwise you'll be taking the derivative of a constant and then you end up at 0 and it just doesn't get you anywhere, right? And so so you want to hold off, even though it's like, oh, I know this, okay, I can just plug those in and then take the derivative. No, that doesn't work. Okay. So we've got these kind of strategies, and so here we go. Let's do our first example. It's that balloon example. So what are these things going to look like? Can I just grab it? I can. Start it on this page. All right. So, and you can have a read through. I've tried to collect all the different kinds of questions. So it's either going to be, you know, some air is being pumped into a balloon, or you have a water tank that's either being filled with water, or it could be leaking water at some rate, right? So kind of same type of question. You might have a ladder leaning against the wall. You might have two objects moving towards each other. So these are all the examples that we'll go through. The only one that I didn't put on here, but it is on the extra practice problems, is a shadow example. So, so maybe have a look at those, but because these are the ones we'll do in class, I want to focus on these ones. So, all right. So just kind of different scenarios that we're going to talk about to death. Okay, so we've got this spherical balloon and air is being pumped into it. So it starts kind of deflated and then air is being pumped into it. And then the volume is increasing at a rate. So here, right? So the volume is increasing at a rate of 100 centimeters cubed per second. Okay. How fast is the radius of the balloon? So how fast, so we're looking for the rate of change of the radius. How fast is the radius of the balloon increasing when the diameter is 5 centimeters? So here we're also given that the diameter is 50 centimeters. 5 centimeters is tiny. Okay. So, okay, let's break this down, right? I have a rate of change of the volume, right? I want to find the rate of change of the radius when, and then we're given the diameter, but if we have the diameter, so we're given, let's talk about the diameter first. The diameter is 50 centimeters, but from there, of course, if we want to talk about the radius, then how about we just convert this? This is easy enough to find that the radius then must be 25 centimeters, right? Some of these kind of basic relationships I do expect you to know, right? So if any of these kind of diameter radius things aren't coming to you very quickly, then maybe review those, but I'll introduce them as they come up here. That one should be okay. So, okay, so really what it's asking is how fast is the radius of the balloon increasing when the radius is 25 centimeters, right? So now we're talking about the volume related to the radius. Okay. So we're also given that the volume increases at a rate, so dV dt, and that's kind of the sneaky part and not obvious when you first start doing these, but the rate of change of the volume with respect to time is going to be 100 centimeters cubed per second. Let's take a step back here and remember, we like these differential operators. Well, we don't like them because they're hard to look at, but they do tell you something about, okay, the volume is in centimeters cubed, And then, so it must be dV dt because this seconds is time, right? And so this is the unit for time, and this is the unit for volume. And so that's a hint at this being dV dt. Okay, so here, these are the units for volume. And this is the unit for time. I guess it's just singular unit for time. So then that's where we get the volume over time, so dV dt. Okay. I will admit, not obvious when you first start reading these problems, right? But we will start to see that pattern where, okay, I can just take that as a rate, okay? And the rate with respect to time, right? Because it's over seconds, okay? So it's increasing, okay? So I do want to say that here, it's increasing at a rate of 100 centimeters per second. So what we do is we use a positive because it's increasing. If it were decreasing, so imagine, you know, you're sucking the air out of the balloon, so now the volume is decreasing. So we need some way to communicate that, because of course then the relationship is different. So here, it's increasing, so we use a positive. So we need to think about that as well. Is this increasing or decreasing? And so this is the rate of change of the volume, the rate of change of the volume with respect to time. Okay. So that's what we're given. And what we want to find is we want to find the rate of change of the radius with respect to time. It has to be time because the rate of change that we have is with respect to time. So and that'll always just be the case. It'll always be with respect to the same thing, but also not obvious, at least to me. We want to find the rate of change of the radius with respect to time. Okay. To match the given dV dt. So we want to find dr dt. And eventually we want to find it when the radius is 25, like we said here, right? But that's the one that I want you to really put off substituting in until the very, very, very end. Even this 100, we're going to hold off on plugging it in until we've done all our derivatives, till we've done all our work. So let's see here. Step one. I guess I could draw a diagram. It's a little bit tricky because I'm not very good at drawing a circle, but draw the relationship. And in this case, it doesn't really do much for me, but what we're saying is there's some volume heading into this thing, and it will affect the radius. In this case, it doesn't, oh, looks like the dv dt is heading into the radius. That's not really the case. Maybe it's heading in here. Right. Drawing the relationship for this one is optional. Sometimes it'll be kind of more helpful. This is a bad one to start with. So when drawing it doesn't really help. But I think when we think about the relationship, it's more obvious than some of the other ones that we're going to do. So step 2 is we want to find a function that relates the volume and the radius. So find a function. Sometimes we have to make that function, but usually we use, that's when we have triangles, then we can make that function. So find a function that relates v and r. Don't worry about the derivatives because that's what we're going to do. We will make derivatives in the next step. Okay. So I'm just going to give it to you, and like I said, it's not a relationship that I expect you to have kind of memorized or anything like that, but 4/3 pi r cubed is the volume of a sphere. Volume of a sphere. Okay. So then, step 3, because I have dv dt, right, there's no getting around that, I want to differentiate with respect to time. Okay, so differentiate both sides with respect to t, and I'll just kind of follow it up here with, since we have dv dt, right, it only makes sense to kind of force this volume function to become something that we know parts of. Okay. So, okay, we want to differentiate both sides with respect to t. So, there are no t's in here, right? So that means that we're going to be using implicit differentiation throughout. The radius is changing with respect to time, the volume is changing with respect to time, but it's all implicit, right? So here I'll write, since there are no t's in the equation, all variables need to be differentiated implicitly. Implicitly. Okay. And that's going to be the case for, I want to say all of these questions. They'll always just be implicit differentiation. So if I differentiate v, oh, how about I'll write out this equation again. V equals 4/3 pi r cubed. So I want to differentiate both sides with respect to t. So I'm going to do this nice and slow. I want to do d dt of v is d dt of 4/3 pi r cubed. Okay, so dv dt comes from, well, the derivative of v with respect to b is just 1, right? But then with respect to t, it's going to become dv dt, right? And so usually we just end up writing dv dt right away if you don't have, v squared or anything like that, right? And so here, the derivative of v is 1 times dv dt. Derivative of the outside, right, times the derivative of the inside with respect to time. Derivative of the inside with respect to time. Right. So it is just the chain rule. Implicit differentiation is just the chain rule, right? And so if you wanted to skip straight to dv dt right away, then that's totally fine. I just want to show you, because that's what I'll be doing in the next few examples, but I just want to show you where things are coming from. So now moving to the right-hand side, 4/3 pi, or 4 pi over 3 rather, is just a constant. So I can bump that to the outside, right? And then what I want to do is I want to find the derivative of r to the power of 3 with respect to time. So 4 pi over 3, I can bump that to the outside, right? The only variable in here is the radius r. So I have d dt of r to the power of 3. I'll do that one in the next step. So 4 pi over 3, just bump that outside. So this becomes 4 pi over 3. Again, the derivative of the outside is 3r squared, right? And then the derivative of the inside with respect to t, this is where we're going to get that dr dt. So this becomes 3r squared times dr dt, right? And I'll just clarify, here's the outside, here's the inside. Okay, so now, pretty fun, right? Because, all right, let's just kind of write out what our total derivative is then. So we have dv dt is equal to 4 pi over 3 times 3r squared times dr dt. Now that I've taken the derivative, now I'm okay to plug in the values that I've been given, right? Because I know that, okay, once I've taken the derivative, then you're free to plug in the values that you know.
Because as we can see here, there's only the one dr dt, and we have values for everything else.
Exactly, right? And you want to be careful, because if we plugged in 25 for the radius up here before we took the derivative of 25 to the power of 3 is 0, because it's just a constant, right? So then we wouldn't get anywhere. So you want to hold off until you've taken the derivative to tease out that dr dt, and now we can plug in all our values, right? And so I can't remember what step 4. Step 4, once we have taken the derivative, we can substitute the given values. Okay. But not until we've taken the derivative. So I'll start here on a fresh page. dv dt is 4 pi over 3 times 3r squared times dr dt. So here, I know dv dt is 100, and that's where you want to pay attention to it being negative or positive. In this example, it's positive, so that's good. 4 pi over 3 times 3 is just a constant, but r is 25. And then here, dr dt is what we actually want to find. Solve for dr dt. Okay. So now I can make these substitutions. So 100 is 4 pi over 3 times 3 times 25 squared times dr dt. Let's just make this a little bit easier on ourselves. 3 over 3 is going to cancel. Right, so we get 4 pi times 25 squared. 25 squared is what? Who knows? 625. So I've got 4 pi times 625. And I want to solve for dr dt. So that means I have to divide both sides by 4 pi 25 squared. So 100 divided by 4 pi times 625 is 25 squared. Or if you want to just keep it 25 squared, that's fine too. Is dr dt. Okay. So if I do 100 divided by 4 times pi times 625, I get a value. And I like to have what I'm solving for on the left-hand side, and that's just a personal hang-up. So I'm going to switch the dr dt to be on the left. Dr dt is approximately, since it's going to be a decimal, 0.01273239545. I never am able to put the brakes on writing out all the decimal places. I don't know. That's okay. There's no harm in writing out all the decimal places. So what are the units here? Well, the units for the radius is centimeters, right? Or I can't remember actually. Is it centimeters? Yeah. So the units for the radius is centimeters, and the units for time, just to match the dv dt, seems to be in seconds. So our units for this rate of change is going to be centimeters per second. All right. This is the units for R, and this is the units for T. So that's how we're able to just kind of quickly get the units for the rate of change. So what we can say is, if we round this to maybe 4 decimal places or something like that, you want to round to something that shows the overall behavior. So it kind of depends on, you know, the magnitude of this number. So there's no hard number to round to, but here I feel like I've captured most of the activity if I go to the 7, and then I can kind of drop off. So therefore, the radius of the balloon is increasing because it's positive, right? Which makes sense. I'm pumping the volume up, and so the radius should be increasing. If you found that it was decreasing, you might want to check that out, right? It should match what you're thinking. So the radius of the balloon is increasing at a rate of approximately 0.0127 centimeters per second when the radius is 25 centimeters. When the radius is 25 centimeters. Now, these concluding statements, you don't need them. I'm just rewording the question as an answer, right? So you don't need to do that, but it just kind of helps summarize it, right? So sometimes I'll do it, and sometimes I'll be so over a question that I don't. Okay. Any questions about that one? Okay. So I haven't seen any. So let's do another example. So I just want to expose you to all the different types of scenarios. The next one is a ladder sliding down a wall. I'll put it on its own page here. And what I want to do is I want to give you like 3 minutes to try this one, just to see where maybe you kind of hit a snag, or I know it's just our second one, so, and your first one, so don't be too hard on yourself, but let's give it a go for about 3 minutes. Even if you're not quite finished, I'll get started and kind of catch up to you. Okay, so we've got a 10-foot long ladder. Now, what I want you to remember is the length of that ladder is not going to change, right? So it's leaning up against the wall, and then it starts slipping, and so and we're given the rate of change that it's sliding away from the wall. Yeah. And we want to find how fast is it sliding on this axis. So you can use whatever notation you want, but let's just start by kind of mapping this thing out. So this problem out. So here, well, I've got, I don't know, the ground, and here I've got the wall. Whenever I can, I'm going to use X and Y, just because for me, it just is a little bit easier to think about. You can use whatever notation you want, right? W and G or whatever, right? And so what we have is, I'll do the ladder here. We've got a 10-foot ladder, which means that now I have this beautiful 90-degree right triangle. Right? So for me, I'm going to denote this distance by X, right? So here on the X-axis in my mind, right, my go-to is going to be X and Y if I can. So unless there's more a kind of obvious notation to use, I'm going to use X and Y. So here's my X, and then I'll denote this distance by Y. Whoops, that didn't look like a Y. But here, right, now that I have this beautiful triangle, I have a really accessible way of relating all these things, right? And so we're also told that this distance is increasing at a rate of 1 foot per second. So you want to think about, okay, when it's sliding down, right, that distance is increasing at some rate, and so the rate has to be positive. So the rate is 1 foot per second. And the rate is going to be positive. Oops, positive because it's increasing. And in terms of the rate, right, here, x, this would be dx dt, right? Because it's how fast is x changing with respect to time. So this is going to be dx dt how fast x is changing with respect to time. Okay. So we have that rate, but really what we're interested in is, okay, so if the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall? So now we need to think about, okay, well, this is actually going to be a negative value. It should become a negative value, right? Because it's sliding down the wall. So y is decreasing with this rate, right? And so here we want to find dy dt. Okay. So we want to find dy dt when x is 6. Right? And of course, dx dt is still 1, positive 1. So whenever we have these, whenever we can, we like using right triangles, right? Because we see the relationship should be by the Pythagorean Theorem. We know that x squared plus y squared equals 10 squared. That's great. I also have dx dt, and I want to find dy dt, so it's nice that I have x and y in here, and that's it, because then when I take the derivative with respect to t, I'll be able to extract those derivatives that I want. So now if I differentiate with respect to t, both sides with respect to t, I'll do it on the outside first. d dt of x squared plus y squared is d dt of a constant of 100. 10 squared is 100, right? So that's just going to go to 0. If you didn't want to write this on the outside first, that's totally fine. You can just go ahead and do the implicit differentiation, right? Which is this next step. So we get 2x, the derivative of the outside, times the derivative of the inside, dx dt, plus the derivative of the outside is 2y, times the derivative of the inside is dy dt is equal to 0. And because I can, I'm going to retroactively stack my equal signs. Make it look nicer. Okay, now that I've taken the derivative, I am free to make substitutions, right? And so let's just figure out what these substitutions will be. Well, I'm trying to solve for dy dt, right? I have dx dt is 1, and I have x should be 6. So let's see what we can get together here. So x is 6, dx dt is 1. And we want to solve for this. Solve for dy dt. We need y. But we already have that relationship figured out, right? But now we're saying, okay, well, when x is 6, the ladder is still 10 feet. So we can figure out what y is, right? So y is going to be from this triangle here. So now I'm forcing x to be 6, y and 10. So 6 squared plus y squared is 10 squared. If you do the math, I'm going to cheat here and say y is going to be 8 when x is 6. Okay. So sometimes we have to do a little bit of work to be able to plug in all the values, but we'll already have those relationships, so we can rely on that to find y in this case. Okay, so I'm going to jot this derivative down here, dx, so 2x dx dt plus 2y dy dt equals 0. Now I can make my substitutions. I get 2 times 6 times 1, dx dt is 1, plus 2 times 8 dy dt is equal to 0. Rearranging, solving for dy dt, I get 2 times 6, putting me at 12. So negative 12, so I get 16 dy dt is equal to negative 12. And you have options, right? You could rearrange this, this kind of default formula before plugging things in, if you find that that's easier, or if you find working with actual numbers easier, then plug in the values and rearrange. Right? After you've taken the derivative, you're safe to plug stuff in either way. So solving for dy dt here, I divide both sides by 16, so I get dy dt is negative 12 over 16. 12 over 16 is going to simplify to 3 over 4. So then dy dt is negative 3 over 4. Let's tack some units on here, mostly to show off, right? What's our units for y? Our units for y are still going to be in feet because it should match our x and the length of our ladder. And time is in seconds. So this is going to be feet per second. And I also want to highlight that it has to be negative, and it makes sense that it's negative because it's sliding down. Sliding down. So y is decreasing at a rate of 3 over 4 feet per second. and I guess that answers, that's kind of the summary blurb too, I think. Let me just scroll back and see how fast is the top of the ladder sliding down the wall when the bottom of the ladder. So I guess we just answered that. I can write it again, but. Therefore, now I've lost the, I'll copy the wording here. The top of the ladder is sliding down the wall at a rate of 3/4 feet per second. Okay. Are you guys okay if we just keep going and then end early? Or do you need a mental break?
I kind of want to just keep going.
Yeah, we're kind of on a roll. Yeah. Let's do it. Okay. That's what I was hoping for. It's kind of the type of stuff you don't want to take a break from, but not in like a fun way. Okay, next question then.
More the kind of thing you don't want to lose a grip on.
Yeah, so here we go. I'll put them on their own pages here. Okay, so here we have the classic inverted circular cone. Pretty much every single final exam that I've ever seen uses an inverted circular cone. And like I said, you can either have water coming in or water coming out, right? So let's see here. All right. So a water tank has the shape of an inverted circular cone with base radius. And so of course the cone, the base radius is the widest part, 2 meters and a height of 4 meters. Okay. So here, let's just draw out this inverted circular cone. And I am not very artistic at all. So I want it to be a nicer cone. How about that? Hey, not bad. So the base radius is going to be this distance here. So the base radius is 2 meters. And the overall height of this inverted cone is 4 meters. So from that base, which is on the top because it's inverted, all the way down to the bottom is a distance of 4 meters. So in this example, what's happening is the water is going in at some rate, at a rate of 2 meters cubed per minute. Okay? So that must be, so meters cubed is volume and minute is time. So that's what tells me that this must be dV dt. Volume, time. So that's what tells me that dV dt is 2 meters cubed per minute. Okay. So what we want to do is we want to find the rate at which the water level is rising when the water is 3 meters deep. So now we're going to have this kind of, and I guess I already used light blue, but the water, right, is going to be rising. So it's going to start empty and then it's going to be rising. But because you have this inverted cone shape, we need to keep that in mind as well, right? And so here, let's just say you've got some pretend water level, and that can change, right, moving up and down depending on at what point in time we're talking about, right? But this is going to have, and now it's really bothering me that I used the light blue already and I had to use green for the water level. Makes no sense. That's okay.
Makes perfect sense. It's just really nasty water.
Yeah, it's just grimy water going in. Yeah, sewage water. So if sewage water is being pumped into, maybe then it'd be like nasty brown or something. If green water is being pumped into the tank at a rate of 2 meters cubed per minute, then what we want to find is we want to find the rate. Let's see, what color can I use here? At which the water level is rising, right? So the water level is going to be the height, right? So here the water level is increasing as we move up this way, right? So the water level, which let's just call that H, right? The height of the water. And what I want to make a note of here is you could have used any variable here. I'm picking H because it makes sense to me, but if you want to call it L or even W, that's fine too, right? So don't be thrown off by the variables that I pick. Sometimes it's just what makes sense to me. So the water level H is what we're interested in, right? So we want to find the rate at which the water level is rising. So again, I expect this to be a positive value when the water is 3 meters deep, okay? So we want to find dH dt dt, mostly because, well, I want the rate of the water level and I already have the volume with respect to time, so it has to be dH dt. There's no other option. When H is 3. Of course, we're going to hold off, just kind of rein it back here. You don't want to make any substitutions until you've taken the derivatives, right? So let's see here. The equation that we're going to use to relate these, and maybe this is a good one to have kind of jotted down, just in case you need to do an inverted circular cone again, which you probably will, right? And so here's one to have in the back of your mind. We know, I'll put it in air quotes because if you had asked me yesterday, I would not have been able to produce this equation. But now I will because I know we're going to use it. So the volume of a cone is 1/3 pi r squared h. So we know the volume of a cone. Okay. So this is probably a good equation to have handy, right? Now this r is not actually talking about this overall radius, right? Because the volume is only talking about the water, right? And so this is the volume, or this is the radius of the water level. Right? So what we can do is we can redraw this, and a trick that we're kind of going to rely on is similar triangles, right? Because I know this length, this overall, the biggest radius that I could have is 2, right? All the other radii are less than 2, right? But also the overall height is 4, right? And then once my water level reaches 4, then I'm done. It's just gonna be overflowing, right? So let's see here. So what we have is we have similar triangles. I'm just gonna go for it. Right, because we have this overall cone. And we said, well, now I'm sticking to it, right? This was 2, and this is 4. And then the water level, let's put the water level on here. The water level has a radius r and a height h. And I'm going to do it on the outside just so I don't kind of cloud there. Okay. So notice that we could rewrite these similar triangles because I know that, I know that if I have a larger triangle here with 2 and 4, and then I have this smaller triangle with the same idea, right? I have R and H, right? I see that 2 is going to be to R as 4 is to H. Okay. So here, 2 is to R as 4 is to H. And maybe that's just something that helps me figure out similar triangles. But what this works out to be is that we're going to write 2 is to R as 4 is to H. So here, 2 is to R as 4 is to H. However you want to get there is fine, right? But this is what I find works for me because sometimes I find similar triangles can be a little bit tricky to kind of master, right? But as long as you kind of think, okay, well, 2 is to R as 4 is to H. Why do we care about this? Well, it's mostly because the radius here in this formula, like we said, is not the radius that we have, that overall radius, right? But I also don't want to be dealing with this R as well as an H, as well as a V, right? And so what we're trying to do is we're trying to rewrite R with respect to, or in terms of H instead, because I want to find dH dt eventually, right? So now we can rewrite R. Therefore, we can rewrite R in terms of H to eliminate R from our equation, right? And only have H's and V's in our equation. So we can rewrite R as in terms of H in order to eliminate r from the equation and only have v and h as our variables. Okay. So what we have, if I want to rewrite and solve for r, right, if 2 over 4 is equal to r over h, then, well, 2 over 4 is 1/2. I can multiply that h over, so then r must be h over 2 after some quick magic there. So now I can use that in my volume equation, right? So now we can substitute this. Now we can subs this into the volume equation. So remember, the volume was, let's see here, 1 over 3, where did it go? 1 over 3 pi r squared h. So I'll write that out first, and then we'll swap our r for the function in terms of h. So 1 over 3 pi r squared h. And now I am going to replace this r with h over 2. So I get v is 1 over 3 pi h over 2 squared times h. Don't forget that squared. H over 2 squared is h squared over 2 squared. 2 squared times 3 is 12, right? 2 squared is 4 times 3 is 12. So I've got a bunch of constants here that I'm going to bump kind of to the outside. So I get v is pi over 12 times h to the power of 2 times h, which is h to the power of 3. So now we have it only in terms of v and h, which is what we wanted, right? And so now we can differentiate with respect to time. So now we can differentiate with respect to time, right? Because I have dv dt and I want to find dh dt, and the only way to get there is if I differentiate with respect to time. So in this one, I'm not going to write out the little steps. I'm just going to do it as if I was doing this problem on my own. And if I was doing that, I would just write dv dt is pi over 12 times 3h squared dh dt. If you wanted to take your time and expand that ddt inside, that's fine. But for me, if I was working on this problem, right, we've already done 2. So if I was doing this problem, I would skip straight to here, right? dv dt, and then bump out your constants, and then differentiate your h with respect to t. Remembering your the derivative of the outside, right? So now we know that, well, I can cancel 3 over 12 is going to be 1 over 4. So let's do that, I guess. My dv dt is 2. It was 2 meters cubed per minute. it's increasing, so the water is increasing, so it's positive. And h, when the height is 3, and maybe I'll do the same thing here, dv dt is 2. And we want to solve for dh dt. Home stretch here, right? So here we go. 2. And like I said, you can rearrange this equation now if you wanted to solve for dh dt, or if you prefer to rearrange with numbers, that's fine too. Does not matter. 2 is pi over 4 times 3 squared. Dh dt. Rearranging and solving for dh dt, I get, well, I'm multiplying across here. 3 squared is 9. So I have to multiply by 4 and divide by 9 pi. So dh dt, doing a complete switcheroo here, becomes 2 times 4 divided by 9 pi. Okay, putting me at dh dt is 8 over 9 pi, which I can 8 divided by 9 times pi, making sure that pi is in the denominator, I get dh dt is roughly 0.2829421211. What's my units? What are my units for this rate? H was in
meters cubed.
meters.
H was in meters. The rate was meters cubed per minute, so it should be meters squared per minute. Oh wait, no, correction. I stand corrected. Yes, meters per minute, because
you already said meters, so I locked it in. Yeah, don't worry. I'll take your first answer, meters. Awesome. Hey, look at you guys go. Awesome. We ready to do our last example for us? All right. Any questions about that one? I've got a page break here, so I'm not going to write a little summary blurb, but you can just reword the question as an answer and then move on. It makes sense that it's positive, right? Because as the water level is rising, right, or as the volume is increasing, the height would be rising, so it should be positive. Good. All right. Let's do this, this last one. This one, it can be, I mean, here we've got cars. It can be 2 people walking towards each other. It can be 2 boats going towards each other. These are all like different situations that I've seen, but the question stays the same, right? How you set up the question stays the same. So here's the situation. So you've got car A is traveling west, right? So it's heading west, and maybe get your never eat shredded wheat situation sorted out, right? And so if it's heading west, I'm gonna put it over like so. So car A is heading west. And then car B, and it helps that I have already worked through this problem, so I know what this graph is going to look like, right? And maybe I should give you just a couple of minutes to try to do the sketch yourselves. Let's just take 2 minutes and try to sketch it out. I've set you up. Now take it home. Not enough time to solve the question for sure, but enough time to maybe set up, kind of tease apart the information that you have here into some sort of, I don't know, sketch. All right. So, like I said, we started off and we said, okay, well, let's say car A is here and it's heading west. Right, and so at some rate, I'm going to hold off on writing down the rate. In fact, I'm going to put this kind of down here in the middle. And then car B is traveling north, but they're heading towards the same intersection. So let's put that intersection here. And car B is heading north, so it must be starting from down here and heading north like that. Okay. Again, I see this kind of XY axis situation. So for me, I'm going to use X and Y as my variables, but you can use A and B if you want. Or west and north, I guess. But for me, I see X's and Y's, and so that's what I'm going to use. So here I'll use, denote this distance as X and this distance as Y. Because A and B are both heading towards this intersection, let's call this intersection C. I know. Wild, right? You don't really need to label the intersection, but it just makes it easier to talk about in general, right? So A and B are both heading towards C, which means that X is going to be decreasing, right? So this rate is actually going to be negative, right? Because X is decreasing, but also Y is decreasing, right? Because B is also moving closer to C, which is making Y smaller. So the rate here, dx dt is negative 50 because it's decreasing. X is decreasing. I'm not going to put units on there, but miles per hour. So X is in miles and time is in hours now. So same thing over here, right? We've got dy dt, kind of a different setup than we had before with the ladder, but we still are going to work with triangles. So that's nice, right? Dy dt is also going to be negative because y is getting smaller as b is moving closer towards c, so it must be negative 60 again because y is decreasing. Okay. So car A is traveling west. Okay, we've got that under control. Car B is traveling north, and we've got both of their rates jotted down on our little sketch here. So both are headed for the intersection of the two roads. At what rate are the cars approaching each other when car A is 0.3 miles and car B is 0.4 miles from the intersection? So okay, the distance from each other is basically the hypotenuse, right? And that's not something that was obvious to me. Well, I mean, when I was learning this, I remember this being kind of a hard thing. But if you just remember that these two things, as soon as you want to try to find how quickly they're approaching each other, right? This is the distance that A is from B, right? You're not going to have to go around through C, right? The distance between them is just going to be the hypotenuse. And just to keep with the X, Y, Z, let's use Z for the hypotenuse. So Z is the distance between A and B. Oops, capital B. Okay. So what do we want to find? We want to find the rate that the cars are approaching each other. Right? So we want to find want to find dz dt when x is 0.3 and y is 0.4. When x is 0.3 and y is 0.4. Okay. The equation that relates all these variables, right, x, y, z, is definitely the Pythagorean theorem, right? X squared plus y squared equals z squared. So let's just put that down and see what we need to do next. So we have the relationship is that x squared plus y squared equals z squared. Okay. And because I have dx dt and dy dt, and I want to find dz dt, well, it makes sense to differentiate with respect to time here. So now I'm going to differentiate with respect to time. Again, it's implicit throughout, right? So I get 2x times dx dt, right? The derivative of the outside times the derivative of the inside, plus 2y dy dt is 2z dz dt. Okay. Looking good, right? So when x is 0.3, when dx dt is negative 50, y, so here I know all of these values, right? X is going to be 0.3, dx dt has to be negative 50, y we were told should be 0.4, dy dt is negative 60, I think. And then we want to solve for dz dt. So the only one that we don't know is z. We need z, but we also need x to be 0.3 and y to be 0.4. So using that original equation, right, x squared plus y squared equals z squared, I can find what z is. So we need z when x is 0.3 and y is 0.4. So let's do that here. I'll use x squared plus y squared equals z squared. So then 0.3 squared plus 0.4 squared equals z squared. I'm just going to skip straight to it. Z becomes 0.5. Right? Okay. We're past that now. We know how to do that. So Z is 0.5. Okay. Woo, woo. Now I have everything that I need to plug this in and to solve for dz dt. So, okay, here we go. I'll just jot down the original here, 2x dx dt plus 2y dy dt is 2z dz dt. What if I mix things up? Usually I would just plug stuff in and then I would solve for dz dt. But now that I have kind of easily available here dz dt, I just need to divide both sides by 2z. So why not? Let's just mix it up a little bit. If you wanted to, you can just plug stuff in here and then solve for dz dt.
I'm just going to point out right here, 2z is actually 1.
Yeah. So yeah, maybe it's more clever to just plug it in here. I was going to divide them and cancel the 2's. What a waste of time. Yeah, with a little bit of foresight, you'll see that 2z just becomes 1. Bada bing, bada boom, you're done. So great. How about I do the harder way? Why not? I already had it set in my mind that I was going to solve for dz dt because it was so available, readily available. So I've got 2x dx dt plus 2y dy dt divided by 2z is dz dt. I can factor out a common 2. Boom, boom, boom. So then, but I did. I made more work for myself than I had to. And here I thought I was saving time. No. Okay, now I'm going to plug stuff in here. So x had to be 0.3. dx dt was negative 50. Make sure you keep those negatives, right? Otherwise, it'll really make a mess. So then plus y was 0.4 times negative 60 divided by 0.5 is dz dt. Doing a little switcheroo, calculating it all out, or pretending to, dz dt is an even negative 78. And what would the units be here? Z is in
miles per hour.
Awesome.
I'm just going to speak up here, though. I hadn't set the 50 and 60 to negative, but when I was examining the little diagram I made further, had the brainwave of, oh wait, but it is going to be a decreasing thing, so I just wrote it down on as, but actually it's negative 78 miles because distance is decreasing.
Awesome. Hey, that's all I'm asking for is just to have that kind of mental check of like, okay, does it being positive make sense? No, it doesn't. Oh, I must have mucked it up somewhere, right? But I'm happy with that. So here, right, I'll just highlight that the distance between A and B is decreasing. And that's related rates. And that's all we're doing today. I think that's plenty. Plenty. So we go through those problems that we did, that I posted. I posted some extra practice problems with the worked out solution. hopefully it makes sense. I didn't actually read through them because they're from class notes from before, but and then definitely watch that Khan Academy video because he does the shadows, and shadows can be kind of tricky. So, but he obviously does a really great job. So, all right. Last section of chapter 3 next day, and then we'll head into chapter 4. And then before you know it, it'll all be over.
Alrighty then. In that case, I shall see you Wednesday.
Have a great weekend, you guys. Let me know if you have any questions. Otherwise, see
Will
you
do.
Wednesday.
Ciao, ciao.